Okay, let's see. So last day of content today, so we've got to wrap up chapter 12, these 3 sections of new content. And then on Tuesday, we'll spend the whole day reviewing for the final. Tuesday after break. After you study for a week during the break, so that you can boost your final grade with that final exam.
God, my in-laws are here.
Uh-oh! Well, you have a good excuse to go study in a cafe. See in-laws?
100%. No, I actually like that.
Oh, well,
Nice.
that's too bad. Then you won't study as much. Okay, so last time we were talking about these polar, oh, I'm in the wrong notebook again. Get to the right notebook, James. All right, so here is the right notebook. So the last thing we had done was taken these couple of polar curves, and we recognized that to graph a vertical or a horizontal line in polar is interesting because you use cosecant if you want a vertical line, and you use secant if you want a horizontal line. So we use these 4 equations to go back and forth between the 2 coordinate systems. And you'll use that a lot in Calc 3 when you get into cylindrical coordinates. Cylindrical coordinates use polar down in the xy plane, and then they use z to go vertically. And then you'll also use those when you get to spherical coordinates in Calc 3. So our next step along this voyage through polar is to look at circles. And we are going to look at circles centered at the origin. And we talked a little bit about this, that when you set r equal to a constant, whether it's positive or negative, you will get a circle of radius absolute value of whatever that number is. So r equals -2 is a circle of radius 2 centered at the origin. R equals 3 is a circle of radius 3 centered at the origin. Well, the general equation for a circle is this right here. And we aren't going to do the general circles. We're going to look at a subset of those to kind of keep it a little bit simpler. We're going to look at either r equals just 2a cosine theta. So in other words, the b is 0. Or we're going to look at r equals 2b sine theta, so the a is 0. And what that leads to is the following. So the most common circles we'll see that don't have an origin as the center will be these 2. So we're looking at this generalized circle, but we're either letting a be 0 or b be 0. So this group of circles will be tangent to the x-axis at the origin. So it looks like that. And if a happened to be negative, it would just be flipped, and it would be below, but still tangent to the x-axis at the origin. Similarly over here, if a is negative, it would be over here. So those are going to be the 2 types of circles we're going to look at, tangent to x or tangent to y. We'll graph a couple of those, make sure that we understand them. So here we go. There's a couple of ways that we can graph these. The easiest way is probably to convert to x and y because we recognize the equation of a circle in the xy world, the Cartesian world. You can also plot polar directly, and let me just show you how I would think about this if we were going to plot it directly instead of converting. When we plot polar directly, we kind of think of this windshield wiper as rotating around, this ray that's rotating all the way around. And normally what we would do is plot this angle, which is 0, and then this angle, which is pi over 2, and then this angle, which is pi, and then this angle, which is 3 pi over 2. So you can kind of just imagine this ray rotating around, and let's see what we get. Sometimes you get enough points that you know what it is. Other times you have to make an educated guess. So if we were to look at this and plug in theta equals 0, sine of 0 is 0. So this would be the origin. Okay? And then we rotate up to pi over 2. Sine of pi over 2 is 1. Multiply by -4, we'll be at -4. So we're right there. And then when we get to pi, sine of pi is 0. So we're back at the origin. When we get to 3 pi over 2, sine of 3 pi over 2 is -1. -1 times -4 is +4, and we go in the direction of 3 pi over 2, which puts us back at this point again. So we're only getting those 2 points when we rotate from 0 to 2 pi. We're only getting those 2 points. Now, I already told you on the last slide that if we have a constant times sine, we are going to have a circle that is centered at, or it's tangent to the x-axis at the origin. So we will get this circle here. That will be the graph of it. But if we do the direct polar kind of method, you're only going to get 2 points unless you pick intermediate angles. So if you know that it's a circle tangent to the origin, that might be enough to do it though. If you look at this and say, oh, I know that a constant times sine or a constant times cosine is a circle tangent to either the x or y axis, those 2 points are actually enough. But if we want to be real definitive, what we will do is the conversion. So when we look at this, we want to convert to x's and y's, and we look here, we're like, okay, well, we have an r sine, but we don't have an r sine over here. What we can do is multiply both sides by r, and if we multiply both sides by r, what we see is that we are going to create a left and a right side that now matches over here. We have an r squared and we have an r sine theta. So this will be, in Cartesian, x squared plus y squared equals -4 times y. R sine theta is y. So there's our Cartesian equation. What we need to do next, one of your favorite activities, complete the square. So we move the 4y to the left, and when we look at the y's, we want to complete the square in y. And so to complete the square, we take the coefficient of y, divide by 2 and square it, we get a 4. So we're going to add 4 to both the left side and the right side. So completing the square like we would do in college algebra. Let me get a little more space here, move down just a smidge. So when we complete the square here, we're going to have x squared plus y plus 2 quantity squared equals 4. Well, there we have it. So this circle has center 0, -2, and it has a radius of 2. And that's what we drew up there. Center 0, -2, and the radius is 2, so that's that circle. So on the exam, if you're asked to convert to the Cartesian equation and then graph it, this is what you would do. Convert it over, put it in standard form, and then you can identify the circle. You can also get a sense of the polar circle by doing what I did with the 0, pi over 2, pi, and 3 pi over 2. So here's another one. So let's first go through the polar graphing method, starting at 0. Start here, theta equals 0. Plug that in. Cosine of 0 is 1. 1 times 2 is 2. So that tells us to plot 2 units from the origin in the direction of 0 radians. So that's this point. Then we come up to pi over 2. Cosine of pi over 2 is 0. So that's the origin. And then we get to pi. Cosine of pi is -1. -1 times 2 is -2. But it's not. So pi is this direction. And if the r value is negative, you flip around and go over here and you're back to that same point. So remember, if r is negative, you plot 180 degrees in the opposite direction. So once again, we're only getting 2 points when we go through the polar method of graphing. But that's enough. If we know that we have a circle tangent to the origin, now we know that we are going to have that circle right there. That'll be our circle. The radius is always half of this number in front. So this one up here had a 4. The radius is half of that. Radius is 2. Okay, so that'll always match. Now if we go the real mathy way, we want to use our equations over there. We have a similar situation. We want to multiply both sides by r so that we have a left side and a right side that lines up over here. R squared is x squared plus y squared. Our cosine theta is x. So that is a pretty straightforward way to get to Cartesian, multiplying both sides by r. And once again, okay, that's a circle, but we don't know where that circle is until we put everything on the left side and complete the square. Divide 2 by 2, we get 1. Square 1, we get 1. So we have to add 1 to both sides. And then we can complete the square. So this is x minus 1 squared plus y squared is equal to 1. That tells us that the center is 1, 0. And it tells us that the radius is equal to 1. And that's what we graphed up there. So those are the types of circles we're going to see mostly. Either centered at the origin, so r equals a constant, or these two special cases where we're tangent to either the x or y axis, tangent at the origin. And if this was a -2, it would just be over there. So a couple of graphing ideas there. So let's take a look at these two equations. These are both polar equations. So here when we see this r here, you should be thinking of it as a function of theta. So you're imagining this theta ray rotating around, and then this r function is plotting a point along that ray, whatever that theta direction happens to be. The r is telling you how far from the origin you are. So this says convert the following equations from polar to Cartesian and then sketch the graphs. So first off, when we look here, we see sine, cosine, and tangent in our equations that convert back and forth. So we don't want these guys. We don't want them. We want to convert to sines, cosines, and tangents. So what we can do here is rewrite cotangent as 1 over tangent. And we can write cosecant as 1 over sine. The first thing I notice here is that if we move the sign to the left, that will give us an r sine theta, which is going to be a y. So let's do that. So we have r sine of theta. And now we have tangent. So tangent is fine. We can just leave tangent there. So converting over, we're going to have y equals, and then tangent is y over x. So the reciprocal of that is x over y. So here is our equation. Now we are in Cartesian. We have that.
Oh, okay.
And this tells us that x is equal to y squared. That'll be our Cartesian equation. Is that okay with everyone? Yeah.
Can you explain again on the what you did for the 1 over tangent theta? I want to say that you did the sine over cosine. I did.
So down here, tangent is y divided by x. So if you have 1 divided by y divided by x, that's
you did the reciprocal.
the reciprocal of that. Yeah.
Gotcha.
Mhm. All right. Now it says to graph this. So when we graph, this is a parabola that opens sideways. So it's opening to the right. There's no domain given here. There's no restriction on the theta. So that means theta can be anything. So we normally normally we're letting theta be anything, but if there was a restriction, then we would have to see if that somehow affected the graph. There's no restriction here though, so we're going to get that whole parabola. This is the equation of a parabola opening sideways. Not obvious. Right? We have to do the conversion, recognize the xy equation. We don't have any intuition for parabolas or lines or anything in polar at this point. Okay, so, but these are the 4 key equations that allow us to convert back and forth. So r equals 3. We've talked about that, and intuitively at this moment you should recognize that that's a circle of radius 3. It's centered at the origin. You should see that already. And so what we talked about on Tuesday was that in this coordinate system where we have r's and thetas, when there's a letter missing, there's no restriction on that letter. So this equation has no theta, so there's no restriction on theta. Theta can be any number. And so we imagine theta, 0 to 2 pi, rotating around. For every angle, r is always 3. So you imagine that theta rotating around, r is always 3. That gives us the circle centered at the origin of radius 3. But that's not the Cartesian equation. So in our mind, we could say, oh, well, we know from algebra that a circle centered at the origin is x squared plus y squared equals r squared. But we want to try to use these equations here. And the trick that we used in the last 2 was to multiply both sides by r. That won't work here. If we multiply the left side by r, yeah, okay, that's good. R squared is x squared plus y squared. But if we multiply the right side by r, we have 3r. We don't have any single r's up here, right? They're all attached to sine or cosine. So that's not going to work, just multiplying by r. But we can do something very similar. If we square both sides, notice what happens. This will give us r squared equals 9. Now we have an equation that has a matching, the variable piece of it matches, and that gives us x squared plus y squared equals 9. That is the Cartesian equation of a circle centered at the origin, because it's just x and y, it's not x minus anything, it's not y minus anything. Radius squared is 9. So that is the circle centered at the origin of radius 3. So there is our graph. The radius of this is 3. And that's supposed to be centered at the origin, maybe there. Radius 3, centered at the origin. Make sense? All right. Now to graph the most interesting polar curve that we're going to look at, the cardioid. Cardioids are going to be the most complicated ones that we are going to do by hand. So cardioid looks like a heart or a kidney bean, depending on where the dimple is. So these are the 4 types of cardioids we're going to look at. So you can have these cardioids that have the dimple on the, sort of horizontal, that direction, or you can have the dimple vertical. Let's talk about these. So these are cardioids. Notice that the one difference that from what we just looked at, let's just wipe these things out for a second. So if we had r equals a cosine theta, we just saw that that's a circle tangent to the origin. Tangent to one of the axes at the origin. Similarly, a sine theta, circle tangent to an axis at the origin. So the only difference here is that if we put a constant out here, then all of a sudden we have a cardioid. So, and it doesn't matter whether, if this could be -2 and -2, 2 and -2, -2 and 2, +2, +2, as long as the magnitude of those 2 numbers is the same, you have a cardioid. So you can play in Desmos with these things and get a good sense of what happens as you fiddle with the coefficients with these 2 constants. So if we graph r equals 3 plus 3 sine of theta, we get that. Now notice if we just start changing these signs, if we make it negative, it flipped it. If we made that one negative, if we make this one negative, nothing changes once we've already flipped it here. What about if we make that positive? That's gonna, what did I do? Put an equal sign. That's just gonna keep it back how it was originally. So this minus sign out here is not doing much. Notice now though that it gets weird if we have different magnitudes for the constants. So let's make this one smaller in magnitude. So that dimple flattens out down there. Looks like that. So there's our cardioid, but if we make it smaller, we get the dimple flattening out. And if we make it bigger, we get a little bubble in the inside. So as you fiddle with these constants, you're just going to change your cardioid into something that's a little, different. Desmos is great for exploring these types of things. So we're just going to look though at the most basic case, straight up cardioid. Now, one thing you're going to notice, we need to have some intuition here to help us with this graphing. And what I want you to do is notice that in all cases here, if you look at the points that I've plotted, so these are in this case, the y-intercepts and the x-intercepts, y-intercepts, x-intercepts, all the way across, x-intercepts, y-intercepts, x-intercepts, y-intercepts. They all form a capital T that may or may not be rotated. So if you look at the 4 points, they're all, if you connect these 4 points with these line segments, you're going to notice that you have a capital T. So I'm going to use that capital T as the guide. If I know where that capital T is, those 4 points are enough to graph the cardioid. As long as you know it's a cardioid, and it's a cardioid if these two constants have the same magnitude and you have just a sine or cosine on the second term. Cardioid. All right? So let's notice with this rotating ray approach that we get these 4 points. So I'm thinking in my head, okay, first start at 0. So 0 radians is right here. And then we plug in 0 here. Cosine of 0 is 1. 2 minus 2 is 0. So that point right there is coming from theta equals 0. So this point right here is theta equals 0. And then we're going to rotate to pi over 2. We plug in pi over 2. Cosine of pi over 2 is 0. 2 minus 0 is 2. So in the pi over 2 direction, we go 2 units away from the origin. All right, so there's theta equals pi over 2. Rotate over to pi. So now we're thinking about going in the pi direction. Plug in pi. Cosine of pi is -1. -1 times -2 is 2. 2 plus 2 is 4. So we plot 4 units away from the origin in the pi direction. So that corresponds to theta equals pi. And the last point we plug in, 3 pi over 2. So we rotate all the way around to 3 pi over 2. So now in the 3 pi over 2 direction, we're going south. Plug in 3 pi over 2. Cosine of 3 pi over 2 is 0. 2 minus 0 is 2. So that says go 2 units away from the origin in the 3 pi over 2 direction. So that's how we get those 4 points. The cardioid, notice that it's very circular. It bubbles out. So it doesn't come in tight here. It's nice and round. And that's how we are going to get all these points. Let's look at one more of these. Let's look at this one. Same idea. Let's see, 0, 3. Yeah, let's do this one. So let's start at 0. So we're going in the 0 direction. We're going east. Plug in 0. Sine of 0 is 0. 3 plus 0 is 3. So we go in the 0 direction. That's positive x-axis, 0 direction. Go east. We're going to go 3 units from the origin, right there. Then we rotate up to pi over 2. Plug in pi over 2. Sine of pi over 2 is 1. 3 times 1 plus 3 is 6. So now we plot the point that's 6 units from the origin in the pi over 2 direction. That's corresponding to theta being pi halves. Then we rotate over to pi. So now we're thinking about going this direction. We're going, what's that, west? Going west. Plug in pi right there, sine of pi is 0. So we end up with 3. So we're going to plot 3 units from the origin in the pi direction. So that's theta equals pi. And then 3 pi over 2. So now we're going down, 3 pi over 2, we're going south. Sine of 3 pi over 2 is -1. -1 times 3 is -3. 3 minus 3 is 0. So there we are at the origin. So that's theta equals 3 pi over 2. So that's how we can graph our cardioids. Figure out those 4 intercepts, and then we just connect them with a nice smooth curve that's very, very round. So let's take a look at some blank canvas here. All right. So we know it's a cardioid because we have constants that have the same magnitude, and it's a sine or a cosine. So that we know it's a cardioid. So let's try this windshield wiper thing, this rotating ray thing. Plugging in 0. Plugging in 0, what do you get? How many? 8. Everyone agree? Cosine of 0 is 1, 4 plus 4 is 8. So that says 8 units from the origin in the 0 radian direction. 0 radian direction is to the right. So we want to come out here to 8. Pi over 2. Plug in pi over 2. What are we getting once we plug in pi over 2? 4. Because cosine of pi over 2 is 0. 4 plus 0 is 4. So in the pi over 2 direction, so going north, we are going 4 units away from the origin. That's right there. And we go to pi. So we started at 0, we did pi over 2, now we're going to do pi. So now we are going west, going to the left. Plug in pi. Cosine of pi is -1. So we end up with 4 minus 4, which is 0. So we're at the origin. So there was theta equals 0. There was theta equals pi over 2. Here's theta equals pi. Now we plug in 3 pi over 2. Cosine of 3 pi over 2 is 0. 4 plus 0 is 4. So we go 4 units in the 3 pi over 2 direction. So there is our capital T on its side, right there. So there are the 4 intercepts. Now we just have to connect those 4 points with a smooth curve, with a dimple that's going to be right there at the origin. And we just have to try to make it round enough because it's more circular. You know, it doesn't come in tight like that. It's very round. So we're going to come out, we're going to try to round this out, sort of like that. Same thing down here. You know, just has to be ballpark. We're not going to get uptight about the tangent lines and where they actually are. That's sufficient. All right, you all try this one then. 2 minus 2 sine theta. You can do it as a chart also. So see if you have mastered the graphing of cardioids yet. So you can kind of do it on the fly on the graph itself once you get comfortable, but if you need to, do a little table, values, and that will help.
This is the 2 is 0%. It was crazy. I did not use the angles to graph that. There. I have like, so this is something.
didn't use the
No, I kind of see something that I can like my own thing. So like for example, you said that so the way that I thought about this, so for example, when it comes to sine and cosine, when they have the same magnitude, one of the points is always going to be at 0. That's a given one.
That's right.
And notice that since they both have the same magnitude, it's always on the same. This is the graph, right? So the magnitude is the same. Let's say that this was 4 minus 4, and this was like for example, so let's go so same thing. The sine right here will let you know if it's going to be on the top or bottom for sine, and cosine is going to be for left and right. That's right. In this case, this is negative, so it's going to be correct. Something that I noticed is that the magnitude or the addition of both these numbers is going to be another point to the So in this case, this is going to be 8. And since they both have the same magnitude, this is going to be 4. That's right. And then
Daría 4 positivo. Da
yeah.
igual, porque es un
And of
símbolo
course, for the labeling,
trabajo,
that's
así
where
que es
I'll go ahead and prove which one.
Yeah, which one
No es
was,
por,
yeah.
es
That's
por la
right.
cantidad de puntitos.
That's like my own way of thinking.
No, that's a good way of thinking about it. Very good way.
I just noticed that.
So when we plug in 0, is everybody on board that we get 2? Plug in 0? We're going to get a 2? So the interesting thing with polar is that we plot the point in that direction. So if r is positive, like it is here, in the 0 direction, we go 2 units away from the origin. Now if that was a negative 2, we would be over here. If r was negative 2, we'd go in the opposite direction. Pi over 2, sine of pi over 2 is 1. 2 minus 2 is 0. So this is going to be a 0. So if we come over to the graph, in the pi over 2 direction, we have a radial value of 0, so that puts us right there. And then we go to pi. Sine of pi is 0. 2 minus 0 is 2. So in the pi direction, we are going 2 units away from the origin. So if you plot your 4 points and you're not getting this t, you know something's wrong. And then the last one, 3 pi over 2, sine of 3 pi over 2 is negative 1, so we get 2 plus 2, so that's 4. And that tells us we are 4 units from the origin in the 3 pi over 2 direction. So we're going to have these. There's going to be our dimple. It's going to come around, kind of roundish. So there is our cardioid. All right. Any questions? So those are the graphs that we're going to look at in this class. Cardioids being the most complicated, circles, cardioids, and some lines. Lines, circles, and cardioids. Okay, last section, Calculus 2. Try. We'll try. Sometimes you just need a mouse. Sometimes you need a mouse. Okay, so we started with parametric on Tuesday. And then when we were finishing up the parametric, we did calculus with the parametric equations. We found slopes of tangent lines. When we think about calculus, that's the first thing you should think of, tangent lines. And now we've introduced this new polar coordinate system. We want to do the same thing. Now we want to figure out the calculus stuff. We want to figure out tangent lines. We want to figure out horizontal and vertical tangent lines. So we have 2 goals. One, tangent lines to the polar curves. And then we want to do the next thing that you think about in calculus, which is area. In calculus 1, you call it the area beneath the curve. For a polar curve, it's a little different. It's not beneath it. It's between the origin and wherever the graph of it is. So it's more of a radial area as opposed to an area beneath a curve. So, dy dx means what it always means, slope of the tangent line. It's the derivative. here's how we're going to find the derivative. Just like in parametric we did dy dt over dx dt. Here we're going to do dy d theta over dx d theta. All right. The strategy, since we already know how to deal with it in parametric, the strategy is actually to take your polar curve and make it parametric. So we're starting with our polar curve, r equals whatever, and we're going to convert it to parametric. Right? So this is dy d theta implies that y is a function of theta and x is a function of theta. So to convert your polar curve to parametric, you're going to take the two standard equations for conversion. X is r cosine theta, y is r sine theta, and up to this moment we've been thinking of that r as typically a constant. When we say r cosine theta, it's like, oh, circle, and that r is like a radial distance. We're going to change our perspective though. Instead of just r, thinking of it as a constant, we are now going to be thinking of it as a function. So when we see those equations that we've been using to convert back and forth, we are not thinking of this r as a function. So when we look at these two equations, r cosine theta, r sine theta, we haven't thought of that r as a function. Now, in the conversion to parametric from polar, we're going to treat that r like it's a function. So here, let's go. Now, you don't need to memorize this. This is just the product rule. We just have to do the product rule. Y prime, we've got two functions here. We've got two functions that are being multiplied together, so we're just using the product rule. R is a function of theta, so we can think of that as our first function. Theta is a function of theta, that's our second function. So we're doing regular product rule. First derivative second plus derivative first times second. For both the numerator and denominator, there's a product rule. So you don't have to memorize this because it's just product rule. Here's what we need to know. So first step, we're going to convert to parametric. So first step, convert to parametric. So x is r cosine theta. So we're replacing the r in our standard conversion equation, replace the r with the function that it is. So our function is r equals 2 cosine theta. So we're going to replace that r with 2 cosine theta, and we're going to do that in both places. So we're replacing the r with what it's equal to. It's a direct substitution. So this gives us, if we simplify this, we'll have 2 cosine squared of theta and 2 sine squared of theta. Now, we come back up here, the numerator is y's derivative as a function of theta, the denominator is x derivative as a function of theta. You can call it y prime or dy d theta, whatever you want to say. So y prime is a function of theta, x prime is a function of theta. We can now do that.
Isn't that just going to be 2 cosine theta sine theta?
Oh, yeah, I didn't do my simplification very good there. That's called bad math. Bad math. Yeah, thank you. So those are our two equations. And if we look up here to find the derivative, we need the derivative of each of those equations. So I'm just going to do them individually. So x prime. So I'll create a derivative system here. So the derivative of x with respect to theta, we have to use the power rule and then the chain rule. So that's going to be 4 cosine of theta to the 1 power. 2 comes down, subtract 1. And then we multiply by the derivative of the base. The derivative of cosine is minus sine of theta. Maybe I'll put that in parentheses here just to emphasize that that minus is coming from that second part. So this will be minus 4 sine theta, cosine theta. All right, so there's our x derivative. And now we'll do our y derivative. Oh, we need a product rule here. So again, we're going to think of this as the first function. This is the second function. So we do first derivative second. So first function, derivative of second is minus sine of theta. So minus, and then we're going to square theta. So there's first derivative second. Plus the derivative of first, which will be 2 cosine theta, multiplied by the second function, which is also cosine, so that's going to give us a square right there. So now we have our two derivatives. We have x's derivative, we have y's derivative, so now we can form dy dx. So dy dx, put the y's in the numerator. And put the x's in the denominator. That is dy dx as a function of theta. If you want to be clever, you maybe recognize those as double angle identities. If you wanted to be clever, you could say that the denominator 2 sine theta cosine theta is sine of 2 theta. So you could write this as negative 2 sine of 2 theta. And in the numerator, we have cosine squared minus sine squared. Cosine squared minus sine squared is cosine of 2 theta. So we would have negative 2 times, let's see, not negative 2, positive 2 times cosine of 2 theta. Because cosine of 2 theta is cosine squared minus sine squared, so the minus is where we need it to be. So if we just factor out the 2, we'd have 2 multiplied by cosine squared minus sine squared. And then you could cancel out the 2. And of course, if you really wanted to get crazy with your simplification, what function is that? Cosine over sine is cotangent. So you could, and we do not have to do this in this class, but you could, if you wanted to, you can simplify it all the way down to that. Now it's not going to matter for us because the main goal is, once we do our conversion, and this question doesn't ask, but the main goal is going to be find dy dx at a particular theta. You could plug in your theta here. Oh, I guess we could have canceled out the 2 here even. So you can plug in that value of theta into whichever equation you want. That's going to be our main goal.
Would that be an acceptable answer for my MATLAB? Because sometimes when
This one?
Yeah.
Yeah.
Okay.
Yeah, it should take that.
Okay.
Now, if I was not going to convert to double angle, I would like to see this simplified at least by canceling out the 2. If you're not going to simplify the double angle, if you're just going to reduce it, then this would be the reduced form without using any double angle identities. So this would be the sort of...
Wouldn't it be negative 2 on the bottom?
I canceled that at 2, so it should be just negative 2. Thank you. Yeah.
And they're multiplied.
Oh!
Yeah.
What the heck? How did they turn into addition? Oh my gosh. I'm like a freshman,
Until it's the end of the semester.
right? Exactly. We got one day of content left. So you could simplify it. Any of those ways is fine. Any of those ways. And so normally, well, we'll see real shortly. But this is how we would find the slope of the tangent line at theta. Let's just do one example here. Let's just suppose we want dy dx evaluated at theta equals, let's see, I'm not going to pick 0 because that's going to give, well, no, let's pick 0. Let's pick 0, and then you can tell me what's happening. So if we plug in 0, sine of 0 is 0, cosine of 0 is 1, so we get 1 divided by 0. What does that mean in terms of the graph, in terms of the tangent line? So the slope is undefined, which means the tangent line is vertical, because a vertical line is the type of line that has an undefined slope. So this means a vertical tangent. So that's undefined, so we have a vertical tangent at theta equals 0. Now theta equals 0, we don't know where that is on the graph until we go back to the equation. So let's come back up here. So theta equals 0, we have a couple of ways to think about where we are. Normally we're going to want to talk about x's and y's, but you could also plug theta equals 0 here and think of it polarly. If you plug in 0, cosine of 0 is 1. 1 times 2 is 2, so we would be at theta equals 0, 2 units away from the origin. All right, so we're over on the x-axis at at the point 2, 0. That's a funny point, right? Because if you think about it in polar, if you think about 2, 0 in polar, and you graph 2, 0 in polar, where are you? Aren't you at the same place you would be if you did 2, 0 in Cartesian? Are you at the same place? Because here the angle, it's r comma theta, the angle is 0 degrees and you're going 2 units from the origin. So you end up at the exact same. So that's one of those anomalies. Normally your polar representation and your Cartesian representation look vastly different normally. But we have some exceptions. So this tells us at that point we're going to have a vertical tangent. So if we look here at the x's and y's, we could also come here. And if you plug in theta equals 0, cosine of 0 is 1, so your x coordinate would be 2. Plug in 0 down here, and your y coordinate, because that will be 0, would be 0. So normally when we say tangent line at a point, we are usually thinking Cartesian. There's a vertical tangent at 2, 0. Now, we have graphed this today already, so why stop here? The graph of that. Okay, it's a constant time sine or cosine. That means it's a circle tangent to one of the axes at the origin. Let's plot 2 points. So when theta is 0, we just plotted the point. When theta is pi over 2, cosine of pi over 2 is 0, that plots the origin. And if we know that it's a circle tangent to one of the axes, we can see right away that, oh, then this is our circle. And yes, we now see that there is in fact a vertical tangent line right there. So that all lines up with what we're expecting. All right. And we see a horizontal tangent line right there. What do you think the angle will be that corresponds to that horizontal tangent line up there? So horizontal tangent line, what do you think that theta would be? So you can envision, I'll draw it in purple right there, you see a horizontal tangent line right there. Say that again?
Root 2 over 2?
So what angle is that? So if you,
Degrees?
either one, degrees or radians.
45 degrees.
45 degrees, pi over 4 radians. That's what it looks like. Let's test. If we come down here and say, well, what's dy dx? What's dy dx at theta equals pi over 4 radians. We just plug pi over 4 in there or there, wherever is the most convenient. Let's plug it in here. So if we plug in pi over 4, sine of pi over 4, you can think of it as root 2 over 2 or 1 over root 2. In this case, thinking of it as 1 over root 2 is a little more convenient because then we're going to square it. And 1 over root 2 is easier to square than root 2 over 2. Either way, when you have 1 over root 2 and you square it, you get 1/2. If you have root 2 over 2 and you square it, you get 2 over 4, which is 1/2. So you end up with negative 1/2 plus 1/2, you will get 0. And in the denominator, what will we get? We'll have 1 over root 2 times 1 over root 2, which is 1/2 times that. So we get negative 1. So this is 0. And that corresponds to a horizontal tangent. Horizontal tangent at theta equals pi over 4. And now if we want to know where that is on the graph, we plug the pi over 4 back in up here. To get the xy coordinates, we'd plug it in here. To get the polar form, we could plug it in there. Visually, we know that it's right there, so we can cut to the chase. It's going to be at 1, 1. So if you plug that pi over 4 in here and here, you're going to get 1 and 1. Plug it in right there, you get 1 over root 2 squared, which is 1/2. 1/2 times 2 is 1. Same thing down there. So this is going to be, the Cartesian point will be 1, 1. And the polar point for that same place, if we wanted to write it in polar, what would it be? Well, we plug in our cosine. We plug in the pi over 4 right there. Cosine of pi over 4 is root 2 over 2. So that's going to just simplify to root 2 for r. And theta is pi over 4. So those are the two representations of that point. Normally we're into the xy. It's, if we say, hey, there's a horizontal tangent at 1, 1, we're thinking Cartesian. Cartesian's easier to describe. We know what that means. Okay, so questions on any of the concepts of what we're doing there? Finding slopes of tangent lines. So our process was to convert to parametric and then form y prime over x prime. That was our strategy. So, what we just did, I would say, is relatively straightforward if you understand that if you're in parametric, you do y prime over x prime and you get the slope of the tangent. There is another way to find dy dx using that horrendous formula. That makes no sense. Right? What we just did was pretty straightforward. Convert to polar, convert from polar to parametric, and then find y prime and x prime and form the fraction. There's not a lot of memorization there. If you wanted to use this formula, you would have to memorize that formula, which would be not advisable. So I would recommend not using this formula. I would recommend use parametric method. But there's some people that love memorizing formulas. Like my youngest child loves memorizing formulas. He has that formula memorized. You do not need it. Okay. So we've got a polar function right there, polar curve. That is the slope of the tangent line. Let's look at a visual here. So let's keep that crazy formula in mind for a second. So if we want the slope of this line right here, we could figure out the angle right there. That would be our theta sub 0. Theta sub 0 is the angle that's going to give you that point of tangency. You just plug it in right there, plug in whatever that theta value is, form this fraction, you got the slope of the tangent line. Or you do what we just did on the last slide. What I want to point out is this special case. If your curve goes through the origin, so you're trying to find the slope of this tangent line down here, if your curve goes through the origin, that is the slope of the tangent line. Tangent of the angle. So whatever that angle is, this whole thing up there reduces to just this for this special case right here. So if you're at the origin, if your curve goes through the origin, this whole thing is going to simplify to just tangent of whatever this angle happens to be for that line right there. Why? Well, right here, your R value is 0. Okay, that R value is 0. So that is going to be what this f. R is the function f. And so these two things right here would be 0 because R is the first coordinate. So these two terms would be gone. And then the f primes will cancel. And then you have sine over cosine, which is tangent. So if you have a special case, it's more of an observation than anything. All right, let's do this. Let's do this. We're going to need more space, so I can already tell. So find the slope of the tangent line to the following polar curves at the given points. All right. So again, my recommendation is let's first convert to parametric. So we'll go in parametric. So we're going to take this curve that's in polar form and we're going to represent it parametrically. So x will be -4 cosine of 2 theta, so that's r, multiplied by cosine of theta. Okay. And then y is same r value, it's the function, multiplied by sine of theta. Okay. Now it's in parametric. That wasn't too crazy. So it's in parametric form. Now we need derivatives. So let's just keep going down here. Let's find our derivatives. So x prime and y prime. We have a product. There's our first function. There's our second function. So we've got to use the product rule. We need the product rule. We're in calculus. Product rule is important. So first function times derivative of second function. Derivative of second function is negative sine of theta. So the negatives will cancel and we will have 4 cosine of 2 theta times sine of 1 theta. So that's first derivative second. Plus the derivative of the first times the second. The derivative of the first. Okay. The cosine's derivative is negative sine. So when we differentiate this, we're going to get a negative. The negative and the negative will make it positive. So we're going to have the 4 in front, and then sine of 2 theta, but then we also have to multiply by the derivative of the angle, so we have to multiply by 2. So we're going to get 8 sine of 2 theta multiplied by the second function. So derivative of first times second is that. Now we have to use the product rule down here. So once again, first derivative second. I said that backwards. Down here, did I say that backwards? No, I said it right. First function times derivative second function. I just didn't take the derivative. So first derivative second. First derivative second. Now the hard part, derivative first times second. The derivative of the first is a little more complicated. So derivative of the first is very similar to what we did here. Derivative of cosine is negative sine of 2 theta multiplied by 2, so that's going to give us 8 sine of 2 theta, just like it did above, times the second function, which is sine of theta. So now we have our two derivatives, x prime and y prime. So, this question doesn't ask for a simplified dy dx. It just says find the slope of the tangent at this given point. We can form dy dx and simplify it, but if it doesn't ask for it, you don't need to. Let's just do it in this case, but if the question really is only interested in the slope at that point, you don't need to simplify this, but we're going to do it this time just for good measure. So y prime over x prime. So we can visualize this here, y prime over x prime, and we can cancel out a 4, I think, right out of the gate, right? Everybody sees that there's a 4 common to both of those. So y prime over x prime, I'm going to divide out a 4. So we're going to end up with minus cosine of 2 theta cosine of theta. Canceled out a 4, so that's going to be plus 2 sine of 2 theta sine of theta. And then denominator x's with a 4 canceled, so cosine of 2 theta sine of 1 theta plus 2 times sine 2 theta cosine 1 theta. So there is our simplified derivative. If we plugged that, if we use that other formula on the prior slide, that's what you would end up with, exactly that. All right, so there is the slope of the tangent to this polar curve. It says find the slope of the tangent at theta equals pi over 2. All right, so we've got that. All we have to do is replace all the thetas with pi over 2 and simplify. So coming in here, let's see, there's going to be some zeros. So right here, sine of 2 theta, if you plug in pi over 2, you get sine of pi. Sine of pi is 0. So this is going to be 0. This is going to be 0. Everyone okay with that? Because we're plugging in pi over 2. Pi over 2 times 2 is pi. So that's gone. Pi over 2 right here into cosine. Cosine of pi over 2 is 0. And so this turns into 0. This turns into 0. This is also going to turn into 0. How about down here? Plugging in pi over 2. Sine of pi over 2 is 1. So that's not 0.
Oh, right.
Right? So the numerator is 0. The denominator is whatever this is at pi over 2. Sine of pi over 2 is 1. Here, when we plug in pi over 2, we get cosine of pi, which is negative 1. So it's really important to know, because 0 over 0 is totally different than 0 over negative 1. 0 over negative 1 is 0. If this was also 0, it's indeterminate, and we would have to take a limit to figure out what the slope of the tangent is. If it's indeterminate, we'd have to do a limit. So that limit, we don't have to think about. This is our slope of the tangent line. So what's our conclusion here? Horizontal tangent, the derivative is 0. So therefore, horizontal tangent at, so when theta is pi over 2, we want to know what is the, we need to be able to say where this is. So if we come right here, x and y tells us where we are. So we're going to plug in pi over 2 right here. Once again, sine of pi over 2 is 1. And cosine of pi is negative 1. So I see a y-coordinate of 4. If I'm doing my arithmetic right. And then an x-coordinate up here, cosine of pi over 2 is 0. So 0, 4. So that's a Cartesian point. I'll put a C here just to emphasize that it's Cartesian and not polar. All right, that's what we have. So this, we don't know the graph of that. All of the graphs that we did that created circles and cardioids, we did not have multiple angles. This is called a multiple angle, right? That's a 2 theta, so it's called a multiple angle. The graph of that's not going to look anything like what we have graphed so far. Let me just show you this and then we'll take our break. So if we look at multiple angles, make things wild and woolly when you're dealing with a polar. So if we graph -4 cosine of double theta, and we need to, I think, I might need parentheses, and I might need to put the R in front. So there's our graph. So when you have multiple angles, you get these graphs that are often called roses. That is what our graph is going to look like. And does it make sense that we got a 0, aka horizontal tangent, where we got the horizontal tangent?
Yes. It's right up at the top.
So we found the horizontal tangent at that point. Whoops, that's not what I want. I want this thing up there so we can see everything. So everybody agree that this makes sense? That that's tracking? So we found that there was a horizontal tangent at 0,4, so that's giving us this horizontal tangent right there. So Cartesian 0,4, horizontal. Sebastian?
The way that you get the Cartesian coordinate was because you plug in the pi/2 on the second coordinate.
Plugging in the pi/2 into the x, we're getting both coordinates. So when we plug in pi/2 right here, we get the x value. When we plug in pi/2 right there, we get the y value.
Gotcha.
So plugging in pi/2 into both x and y. All right, let's take our 10-minute break. And then we'll find some area of polar regions. Let's see. All right, let's do one more example of this type of thing. So we have this curve here, 4 plus sine theta. That's not a cardioid because those coefficients don't have the same magnitude. So if this was 4 plus or minus 4 sine theta, then it would be a cardioid. It's not a cardioid. It's one of those modified cardioids where there's a bubble on the inside or something like that. So we could graph it in Desmos if we cared. We don't care right now. We'll graph it maybe at the end. So our process to find the slope of the tangent line at these two polar points, we're going to convert to parametric, find dy dx, and then plug in the theta. So converting to parametric, we have x equals r cosine theta. And we have y equals r sine theta. So those are the two parametric equations. So we're done. Now it's in parametric. And once it's in parametric, we have to find a derivative for both x and y. Once again, we've got a product. So we use the product rule. First derivative, second. So first, derivative second, plus the derivative of first multiplied by second. Well, second is also cosine, so this becomes cosine squared. And then we do the same thing for the y function. Take its derivative, we need the product rule. So we'll do first derivative second. So first, derivative second, plus the derivative of first is cosine times the second. So there is our pair of derivatives. And if we want to, again, you don't always have to simplify this, but if we want to, this would be y prime over x prime. So this is going to be 4 cosine theta plus, so I'm distributing here, plus. Notice that with the y prime, when we distribute the cosine, we get sine cosine, and then here we have sine cosine. So that's going to be 2 sine cosine. So there's y prime. And then x prime looks like we are going to have minus 4 sine theta. And then minus sine squared plus cosine squared. So there's our, there we are. If we wanted to, we could go to double angles. Let's not do that. So there's our simplified dy dx. That's the slope of the tangent line. And now we want to evaluate. This problem said find the slope of the tangent line at these 2 points. These points are in polar. So again, it'd be nice if they put the little p, but they don't. So 4, 0. So what is the theta value for this point up here, 4, 0?
0.
Theta is 0. So that's what we're going to do. So we're going to find dy dx at theta equals 0. In the numerator, we know that sine of 0 is 0. Cosine of 0 is 1, so the numerator becomes 4. In the denominator, sine of 0 is 0, sine of 0 is 0, so that's gone. Cosine of 0 is 1, so we get a slope of the tangent line being 4. And then they also said find dy dx at another polar point. The other polar point, theta is 3 pi over 2, so we're going to plug in 3 pi over 2. Three pi over 2 here, cosine of 3 pi over 2 is 0. Cosine of 3 pi over 2 is 0, so the numerator is 0. Let's see about the denominator. Cosine of 3 pi over 2 is 0 again, so that's gone. Sine of 3 pi over 2, negative 1. Sine of 3 pi over 2 is negative 1. So negative 1 times negative 4 is 4. And then minus, negative 1 squared is positive 1. So we have 0 divided by 3, which is 0. So this means horizontal tangent. Horizontal tangent. And if we want to know where that horizontal tangent is, we have to come back up to the x and y and plug in the 3 pi over 2 up here. Plug in 3 pi over 2 up here, cosine of 3 pi over 2, that's 0, so x is 0. And then sine of 3 pi over 2 is negative 1, so it's going to be 3 times negative 1, so negative 3. So this would be at 0, negative 3, and this is Cartesian. So let's and this slope of 4 here, let's just notice where that's at too. Might as well. So where is this? The slope of 4 is at. So we're going to plug in our angle of 0 here. Cosine of 0 is 1. Sine of 0 is 0. So this is going to be 4. Plug in 0 down here. Sine of 0 is 0. So this is at 4, 0. And that's in Cartesian. So let's graph our curve and just get a sense. 4 plus sine of theta. 4 plus sine of theta. So r equals 4 plus sine theta. All right, so there's our graph. Certainly looks like a circle. What do you think? Do you think it's a circle? I'm not convinced, but
It's a little old, right? It has a shape of a circle. It's a little long.
all right. Maybe I'll figure out
I'm not gonna.
right after class if it's really a circle or
Just
not.
the shape is a circle. That's-
Okay, so let's just summarize this here. So at
It makes
4
sense.
comma 0, the slope is 4. Does that track with what we're looking at? So 4 comma 0 is right here. If we drew the tangent line right there, what this is saying is that that slope is 4. That makes sense. That looks like it's in the ballpark. And then at 0 comma negative 3, so that's down here, we found that there was a horizontal tangent, and yeah, that tracks. Just have a hard time believing it's a circle.
Well, it's a tiny bit wider than it is tall.
It is, right?
Yeah.
Like right here, if we look right there, that's 4 and change and 4 and change. Whereas from here, that's exactly 4 and exactly 4. So yeah, it's a little bit like an egg. A very round egg.
It's round.
Is it ducks that make round eggs? Who makes round eggs? Ostriches. Ostriches make pretty round eggs. Okay. Any questions on any of the steps in this process here? I feel like that slide got really long. Should break that into 2 slides, I think. No, maybe not. Maybe it's okay. All right. Any questions on that process? So, let's move on to this slide. So this says find the points at which the following polar curves have horizontal or vertical tangents. That we know is a circle. We've talked about that one already. So we think of it as a circle that's either tangent to one of the axes, x or y, at the origin. And once you've done a few of them, you probably know which axis it's tangent to. You'll see it's tangent to the x-axis. Let's do a quick graph of it just as a reminder. So if we know it's a circle tangent to one of the axes, we can get away with just 2 points. That'll be enough. We can do it. So let's do our polar method of graphing. 0, sine of 0, 0. So that plots the origin. Pi over 2, sine of pi over 2. 1. 1 times negative 2 is negative 2. So we go negative 2. So we go in the opposite direction 2 units. So this is going to be a picture of our graph. We have this. Ooh. Now
that's an egg.
that's an egg. that is an egg.
It wouldn't give you a circle. It's like, no.
Not a circle. Okay, so it's supposed to be a circle, even though it looks a little goofy, but it's not to scale. Okay, so knowing that it's a circle, we should expect 2 verticals and 2 horizontals. All right, so let's go ahead and do that. So first we're going to convert to parametric. So x is going to be r cosine theta. Y is going to be r sine theta. So there's our parametric. I'll rewrite it simplified here. So we have negative 2 sine theta cosine theta. We could go double angled. We don't need to, so let's not do it. So there are the parametric equations for that circle. If you graph these parametric equations in Desmos, you're going to get that exact same circle. So it's the parametric representation of that circle. Let's go to derivatives. So now we need the derivative of x and the derivative of y. X we need to use a product rule. So we're going to do first derivative second. So the first function is 2 sine of theta. The derivative of the second function is minus sine of theta, so that gives us positive 2 sine squared of theta. So first derivative second. So I'm thinking of this as first, that is second. First derivative second. Now we do derivative first, so minus 2 cosine of theta times cosine of theta, so minus 2 cosine squared of theta.
Imagine that's a circle.
Say that again?
No, I'm just saying imagine that as a circle.
Okay. And then the y prime, not a big deal here. We'll use the power rule first, so negative 4 sine of theta. So the 2's coming down, subtracting 1, but then we have the base. The base is sine theta. We have to differentiate that. That's cosine. So we've got that. Okay, now here's an example where they don't even mention dy dx. We know that dy dx is y prime divided by x prime. We don't need to put it down here and simplify if we don't want. You could just sort of focus on, well, when the denominator is 0, we have vertical tangents as long as the numerator is not simultaneously 0. So if the numerator is 0 and the denominator is not, then we definitely have a horizontal tangent. And if the denominator is 0 and the numerator is not, we definitely have a vertical tangent. But if both are 0, it's indeterminate and we'd have to do extra work. So we'll write this just because it's pretty easy to do in this case. We'll cancel out a 2. So we're going to have minus 2 sine theta cosine theta. Dividing out a 2, and if we divide out a 2 in the bottom, we'll get sine squared minus cosine squared. And if you wanted to, you could say, hey, let's push the minus into the denominator so that we have double angle identities really exactly in both places. Don't have to, but this is going to be sine of 2 theta in the top, and that's going to be cosine of 2 theta in the bottom. So this whole thing, if we wanted to, we could write this as tangent of 2 theta if we wanted to switch over. Don't have to, though. So we are fine simplifying right here even. It's totally fine. Okay, so now the question asked us to figure out, with that, use a mouse. So the question said, find the vertical and horizontal tangents. So let's figure out when these are both 0. Right, that's what we need to know. We need to know when those are both 0. So the numerator when is that 0? So that's a product. So it's going to be 0 whenever either sine or cosine is 0. Right. So that tells us that the numerator is 0 at theta equals, we're just going to go 0 to 2 pi. So it's going to be theta equals 0, theta equals pi over 2, theta equals pi, theta equals 3 pi over 2. And we're not going to include 2 pi because that's just back to 0. So everybody agreed that that's where the numerator is 0? All right, so sine is 0 here, cosine is 0 here, sine is 0 there, cosine 0 down at 3 pi over 2. Now the denominator. So now we look at the denominator. That equal to 0. That's going to be when sine and cosine have the same value, same magnitude. You agree? Like if sine, because these are both squared, so it doesn't matter whether we're in quadrant 1, 2, 3, or 4. They have to have the same magnitude though, in order to make that 0. So sine has to be equal to cosine, or sine has to be equal to minus cosine. So that's going to give us pi over 4, 3 pi over 4, you know, those things. The corners, the diagonals. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. We're going to agree with that? Okay. Now, there's no overlap. So that's good. We don't have to worry about that indeterminate form where both top and bottom are 0. But it seems a little fishy. We sort of look over here and we see 2 verticals, we see 2 horizontals. So here's the next question. Should we really be considering all of those options? And let's go to Desmos for a second. What was our graph? Minus 2 sine theta?
Yeah.
So if we look at this, notice down here, if I go 2 pi, all right, we get the full circle. If we go just pi, we get the full circle too. So the domain to graph one circle and not any overlap is actually 0 to pi. Right? So like if I go pi over 2, I'm getting half the circle. So the domain here is actually only 0 to pi, not 0 to 2 pi.
Is there a way to figure that out without using Desmos?
Yes. So so Desmos gives us a good visual for it. Remember when I graphed this, I only got 2 points? Like we graphed theta equals 0 and got the origin, and then theta equals pi over 2 and we got down there. So that's actually sort of cluing us in that when we got over to pi, we're back to this point, so we already are repeating ourselves. So it starts to repeat at pi, not 2 pi. So that's sort of our clue that, oh, we don't really need, once we see the graph, that's a clue that we have too many angles here. And when we did our graphing with that polar method, and we actually ended up with just 2 points for those 4 angles that we substituted in, 0, pi over 2, pi, and 3 pi over 2, we only got 2 points. So that tells us that we're repeating ourselves and that the period is actually pi. So these guys we are going to ignore because the domain is 0 to pi. This will be the domain to graph exactly one loop of the circle with no overlap. We're going to exclude pi because it's going to plot the same point as 0 would plot. All right, so that tells us then that we have our conclusion here. So therefore, when the numerator is 0, that's corresponding to a derivative of 0, which is corresponding to horizontal. So we have horizontal tangent at 0 and pi over 2. And this is theta. I'll write theta equals 0 or pi over 2. And we have a vertical tangent at theta equals pi over 4 or 3 pi over 4. Okay, so that's all tracking. So this says find the points. Those are angles. So now let's correspond this to points. So let's see, what are these 2 points? When theta is 0, we come up to our equation right here, our parametric form. Come up here. I guess here's our simplified form. So when theta is 0, what is the Cartesian point?
0, comma.
0 comma 0? Because sine of 0 is 0.
Yeah.
So both those turn into zeros. The Cartesian point, when theta is pi over 2, we come up here. Cosine of pi over 2 is 0. sine of pi over 2 is 1, so negative 2, so 0 comma negative 2. So this is Cartesian. So we come over here. Here are the two horizontals. 0 comma negative 2 and 0 comma 0. Those are our horizontals. And then let's go purple for the verticals. So vertical, pi over 4. So we come up here, pi over 4. Plug in pi over 4 up here for the x-coordinates, sine of pi over 4, 1 over root 2, 1 over root 2, so that's a half, so that's going to be negative 1, comma, down here, pi over 4, in there, sine of pi over 4 is 1 over root 2, you square it, you get 1/2, you get negative 1. So negative 1 comma negative 1. And then 3 pi over 4, same idea. Up here, sine of 3 pi over 4 is 1 over root 2 and negative 1 over root 2. So it's positive 1. And then 3 pi over 4 down here, sine of 3 pi over 4, 1 over root 2 again. Square it, you get 1/2, you get negative 1. So let's see if that tracks. So negative 1 is right here. And 1 comma negative 1 is right here. So that all tracks. There's our vertical tangent on the left. There's our vertical tangent on the right. There we have it. So these are our conclusions right here. And these points, it's helpful to put a little C or a little P if you're get a little, it's a little easier to keep track, I think. Okay. One more of these. This thing, what is the graph of that?
It's a cardioid.
Cardioid, right? So we've got the heart, got the cardioid. Let's plot it. So we'll do the polar plotting. We're going to look for our guide, which is the capital T. So let's look for our guide. So start at 0. Sine of 0 is 0. Negative 3. So in the 0 direction, we want to go negative 3. So that means bounce backwards over here. So that is theta equals 0. Pi over 2. Sine of pi over 2 is 1. Negative 3 is negative 6. So in the pi over 2 direction, negative 6. That means down here. 1, 2, 3, 4, 5, 6. So that's a pi over 2. Now we go to pi. Sine of pi is 0. So in the pi direction, go negative 3. All right, that really means go 3 this way. We already know where the last point's going to be, but let's finish it off. Sine of 3 pi over 2 is negative 1. So we end up with 3 minus 3, which is 0. Puts it right there. So our cardioid is going to look roughly like that. How many horizontal tangents do you see? So certainly one down there. These points are different, aren't they? So you see 3 horizontal tangents. Because we talk about the tangent line at a point. So the tangent line at this point is different than the tangent line at this point. All right. So we see 3 horizontals. Now let's go verticals. How many verticals do you see?
2.
So we definitely see these 2. Now that dimple thing. If we look at that dimple thing in Desmos, you get a better view. So, was it negative 3, sine of theta? And we're going to go to 0 to 2 pi to get the whole thing. So this one has a period of 2 pi. If we go less than 2 pi, we're only getting part of it. So we definitely want 0 to 2 pi. And if you zoom in on that dimple thing, you think it should at least be plausible that there's a vertical tangent line there. And if you look in your book, they will go through the math here to confirm that wherever your dimple is, if your dimple is on the y-axis, it's actually a vertical tangent. And if your dimple is on the x-axis, it's actually a horizontal tangent. So you'd have to use a limit to do it. We're not going to go through that detail. It's a little bit tedious. But suffice it to say that you will always have the same number of vertical and horizontals. You will always have the same. There will always be 3 for a cardioid. Always 3 horizontal, always 3 vertical. All right, to prove that, you have to use limits, and it's a pitta. We won't do it. Okay, so let's find, first, convert to parametric. So the x-coordinate is going to be r, which is now a function, times cosine theta. Y is r times sine of theta. There they are. Okay, so we need the derivatives. So let's go ahead and do that. Yes, we have to use product rule again. It should be familiar to you by now. It's a known pain that we experience. So first derivative second. Plus the derivative of the first times the second. I guess I can put a plus and just put parentheses. So derivative of first is going to be minus 3 cosine theta times the second. Oh, that puts a cosine squared. Let's actually get rid of that plus. Let's make that neater looking. So we have that. And then for the second one, same thing, product rule. So we do first, derivative second, plus the derivative of the first, which is minus 3 sine of theta. Derivative, that's cosine. Derivative, so minus 3 cosine theta times sine of theta. So there's our y prime and our x prime. All right, let's not write down dy dx this time. Let's just cut to the chase. So let's set x prime. So x prime is the denominator. So when x prime is 0, that's targeting horizontal asymptotes. Did I say that right? No. When x prime, which is in the denominator, is 0, when the denominator is 0, we're targeting vertical tangents, because when the denominator is 0, we have an undefined derivative. So let's do x prime equals 0. So here we're targeting vertical tangents. So targeting vertical tangents. So x prime equals 0. So we're going to set that to 0. So 0 equals this. I'm going to multiply it out. So we have 3 sine of theta plus 3 sine squared of theta minus 3 cosine squared of theta. Oh boy. There are 2 trig functions. If we want to figure out what theta is, unless you can factor, so you've got 2 factors with the trig functions separated, 2 trig functions is no good. We want to convert one to the other so that we can have 1 trig function. This one is the one to convert, because we can convert that easy. We could convert this easy, but we can't convert that easy. So this one we are going to write as 1 minus sine squared of theta. That's what we're going to do with that cosine squared. Okay. Notice that we can divide 3 away, right? Because 0 is on the left. 0 divided by 3 is still 0. So this right-hand side becomes, when we simplify it, we have sine of theta. And then over here we have sine squared times 1. So it's sine squared. If we distribute the 1, oh, we're only distributing the minus. We're not distributing the sine squared. Okay, I got confused there. So it's sine squared plus sine squared. So 2 sine squared. Am I adding correctly? And then minus 1. So sine squared, but then we distribute the minus sign. We have minus 1 plus sine squared, so we have 2 sine squared minus 1. We are going to reorder this so that we can factor. So that we have 2 sine squared of theta plus sine of theta minus 1. We're praying that this will factor easily. Our prayers have been answered because all of our, this leading coefficient's prime, so we have 2 and 1, there's no other choice. The tail is 1 and 1, there's no other choice. We need a positive in the middle, so we're going to put a plus here and a minus there, so that we have 2 sine of theta minus 1 sine of theta, so that matches with the middle. So this tells us that sine of theta is equal to 1/2 or neg 1. Zero product rule. When we look at the unit circle, which makes things a lot easier if you know your unit circle well. So sine equals 1/2 means the y-coordinate is 1/2. So we're looking from 0 to 2 pi. So that's where sine is 1/2. Sine is equal to negative 1 down here. So we have 3 angles. So our 3 angles are theta equals pi divided by 6, 5 pi divided by 6, and 3 pi over 2. So that's where our vertical tangents are, at those angles. That's where our VTs are. So the purple, those angles. All right. Now this thing, it asks for the points. So if we want to figure out the corresponding points, we're going to plug in the angle right up here, get our x and y points. That'll give us our coordinates. So the 3 verticals are going to be at, plugging in pi over 6, we would simplify this. Cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. So we'd have to simplify this. Maybe I'll find those coordinates after class ends so that we don't spend time doing all that arithmetic. But we are going to have 3 points here. And I will get them by plugging in the pi over 6, the 5 pi over 6, and the 3 pi over 2 right here. Right. Let's find the other ones. So y prime equals 0. This is going to correspond to horizontal tangents. So horizontal tangents are where the numerator is 0. The numerator is that thing, y prime. That's the numerator. So we want to set that equal to 0. So we have negative 3 cosine theta minus 3 sine theta cosine theta. Minus 3 sine theta cosine theta. First thing we'll do is ditch the 3's, so we're going to divide out 3. And we can divide out negative 3 actually. So let's make this all positive. So divide out negative 3. So then this all becomes cosine of theta. And these are the same, right? Sine theta, cosine theta, sine theta, cosine theta. So plus 2 sine theta, cosine theta. Here we're extremely happy because we can turn this into multiplication without much trouble. So we don't have to deal with converting one trig function to the other because we can separate them with multiplication. This tells us that cosine of theta is 0, or sine of theta is neg 1/2. And if we go to our unit circle and figure out what the angles are that generate those values, cosine theta is 0, there and there. Sine of theta is negative 1/2 here and here. And what do we notice? We have 4 angles, not 3. What we notice is that this 3 pi over 2 is duplicated. So let me write them over here. So theta is going to be pi over 2, 7 pi over 6, 3 pi over 2, and then 11 pi over 6. This one is duplicated. Okay. So these other 3 automatically are generating horizontal tangents. The 3 pi over 2 is creating indeterminate form, and you would have to use a limit, and what you find out when you take the limit is that this is the one that is true. This is extraneous down here, not creating a horizontal tangent. It really goes up there creating a vertical tangent. So that when you do the limit, that's what you would figure out. Now we know, we already talked about it informally, that for a cardioid, we're going to get that as a vertical tangent here. So that one is going to be extraneous, and we are going to have 3 points over here that correspond to those 3 angles. I will figure out the coordinates of those points and put them in here. But to get those points, you're just plugging your angles in here and then doing the simplification, which is a little bit tedious. So I will do it after. So is there any question on the process? We've got our polar curve, convert it to parametric, find dy dx, numerator being 0 leads to horizontal tangents, denominator being 0 leads to vertical tangents. So that process is the same as what you did in Calc 1. So our final topic. Our final topic is finding the area between the origin and a polar curve. So polar curves, the way the points are plotted, you've got a rotating ray, and then your points are plotted a particular distance from the origin along that rotating ray. So in your mind, when you plot a polar curve, you're imagining this rotating ray, and then you're plotting a bunch of points that are a particular distance from the origin. So they look like sectors. So down here we have the sector of a circle, and the area of a sector of a circle is right there, 1/2 r squared times theta. That's the area of a circle, the sector of a circle. In Calc 1, you used rectangles to approximate area beneath a curve. You had a bunch of rectangles. In polar, what you're envisioning is a bunch of sectors. So a bunch of slices of pizza, essentially. A bunch of sectors. And just like in Calc 1, here we're not going to go through the nitty-gritty and look at left-hand points and right-hand points and all that business. What we know is that as the number of sectors increases, that little angle gets smaller and smaller and smaller. It's going to 0. And if you add them all together, you get a Riemann sum. This Riemann sum approximates the area. So each one of these is the area of a sector. The area of a sector is 1/2 r squared times the little angle. And if you take the limit of that thing, you learned in Calc 1 that the limit of a Riemann sum is the definite integral. So we just wave our hands in this class when it comes to Riemann sums. Wave our hands, poof, we've got an integral. So it turns into an integral. So here's a picture of a general polar region. Now they generalized it right out of the gate. Let's pause on that for a second and come down here. So if we just have a polar curve and we just want the area between the polar curve and the origin, so this polar region in here, all we do is integrate 1/2 r squared d theta. So we take that. This is what the Riemann sum will give us. The limit of the Riemann sum will give us that integral. What they've done in this book is generalized it right out of the gate. They say, hey, let's find the area between two polar curves. Well, then you do the same thing that we did back with the washer method. You find the area between the outer curve and the origin, you find the area between the inner curve and the origin, and you take the difference. And that's why we have the subtraction. So we take the outer function, square it, take the inner function, square it, take the difference. So it's very similar to the washer method where you took the outer area, took the inner area, and took the difference. So that is our generalized formula for the area between two polar curves. If we just have a simple polar region, so just one curve, that's our area, 1/2 r squared d theta. So let's try it. Let's see if we can find the area of some polar regions. All right. So in Calc 1, you always wanted to avoid integrating through points of non-differentiability. Like if you had a cusp for a corner or something, you always wanted to avoid that. And that's generally a very good rule. When you're integrating in polar, sometimes you can integrate right through intersections, sometimes you can integrate right through vertical tangents. There's no rule. You can't tell. The best strategy is to avoid all those corners and vertical tangents just in case. Just in case. It's better to be safe than sorry. Because most of the time you can do it, but sometimes you can't. So in other words, this says find the area inside the right lobe of that function. That function creates this object that's called the lemniscate, which is the infinity symbol. And we want the area that's inside the right side. So we're trying to find this area. But if we could find the area of this here, we could double it. So if we can reduce and get down to the smallest piece possible and then use symmetry, that's going to be the safest bet. And when we look at our function here, if we plug in theta equals 0, we are right here. So theta equals 0 plots that point. And then theta starts rotating. And we need to figure out, well, when, so points are being plotted along this curve as theta is rotating. So right here, it looks to me like the origin will be plotted when we're at pi over 4. Right? Do you see there's the pi over 4 radial line right there? And it looks like that's when we're going to get to the origin. So we can confirm this if we go into Desmos, put in this function and graph from 0 to pi over 4. We'll get the top half of that eyeball thing. And if you start going between pi over 4 and pi over 2, you are not going to get any points on this graph. So 0 to pi over 4 is going to graph this thing right there. So what we are going to do is say that the area will be 2 times the integral from 0 to pi over 4, 1/2 r squared d theta. And then our function is going to get plugged in for that r value. So this is going to, the 2.5 simplify. We're going to get pi over 4 up here. And when we square this, we get cosine of 2 theta. So we substitute the curve in for r. We're going to use symmetry. So this 2 right here is by symmetry. And then we have this integral of cosine 2 theta, which we know how to do. That's sine of 2 theta over 2. from 0 to pi fourths. Plugging in 0 gives us nothing, because sine of 0 is 0. So we just have to plug in pi over 4. Plugging in pi over 4 gives sine of pi halves. Sine of pi over 2 is 1. So this is going to be 1/2. So that is the area of the right eyeball, the whole eyeball. So we have a new formula, 1/2 r squared d theta. That's our new formula. Let's try it down here. Cardioid. Right? Everyone recognize that as a cardioid now? We've got those matching coefficients, sine or cosine, adding or subtracting, doesn't matter. Let's graph it with the T method. Plugging in 0, sine of 0 is 0, so we're at 4. Pi over 2, sine of pi over 2 is 1, so we get 8, so we're up there. We kind of already know what's going to happen. Plug in pi, sine of pi is 0, so we go 4 in the pi direction. 3 pi over 2, we're going to get 0. So this is going to be our cardioid. It's going to bubble out like that. Not great, but that's fine. So there's our cardioid. Yeah?
So how do we get the 1/2 r squared formula to begin with?
Because that's the area of a sector of a circle. So back in algebra, you learned that the area of a sector is 1/2 theta r squared. So that's from pre-calc.
Okay.
And the way that you do it, tell me what the area of a circle is.
Half pi r squared theta.
Area of a full circle is pi r squared. So the area of a full circle is pi r squared, and if we take a portion, if we take a ratio, so if we call this theta, what is the circumference of the circle?
2 pi r.
The circumference is 2 pi r. Let's take out the r for a second. If we go all the way around, what is theta? 2 pi. So we want to multiply, so we can think of that as a fraction of the circle. So pi r squared is the full area, and then we want a ratio of it, like a half of it, or a third of it, or a fourth of it. If we do theta divided by 2 pi, that is the fraction of the circle that is this sector. So we're taking a fraction of it. Theta divided by the full circle gives us a ratio of the full circle. And then the pi's cancel, and we get 1/2 theta r squared. And then for us, we put the theta on the end because theta is going to be our angle that's going to be getting tinier and tinier.
And that would be represented by the
D theta.
Okay.
Yeah, exactly. So here it says find the area of the full cardioid. When we look at this dimple here is our potential bad point. And we know that we could use symmetry here. We have two choices. We could find that area, which would be negative pi over 2 to pi over 2, and double it. Or we could go from pi over 2 to 3 pi over 2 and double it. We could do either. Does not matter. Let's go with 2 for symmetry. The one that's a little more intuitive maybe is integrating from pi over 2 to 3 pi over 2. So let's go pi over 2 to 3 pi over 2. And then we have 1/2 r squared. So the function in this case is the cardioid. And then we have to square it, and then we have d theta. The 2's cancel. So we have the integral from pi over 2 to 3 pi over 2. Squaring this out gives 16 plus 32 sine of theta plus 16 sine squared of theta d theta. Okay. Power reduction. Anytime we have a sine squared or a cosine squared, we need to power reduce in order to integrate. So let's do our power reduction identity for that sine squared piece of this. So the power reduction is going to give us, so 1/2, so that's going to turn that into an 8, 1/2, 1 minus cosine of 2 theta. So that's power reduction back from chapter, whatever it was. 8? Did we start in chapter 8? I can't remember anymore.
6?
6? Maybe it was chapter 6. So then let's factor out an 8 here. So if we factor out an 8, we're going to get 2 plus 4 sine of theta. We factored out the 8. So then plus 1 minus cosine of 2 theta. All right, that we can integrate. We can combine those two constants and integrate. We're good at that. So 3, we integrate that, we get 3 theta. We integrate sine and get negative cosine. We integrate cosine and we get sine of 2 theta divided by 2, and that's going to remain negative. And then we're going from pi over 2 to 3 pi over 2. Cosine of pi over 2, 0. Cosine of 3 pi over 2, 0.
How'd you get 3 theta?
3 theta, 2 plus
Oh,
1.
there's the 1. Okay.
2 plus 1 is a constant of 3. Integrate that thing 3 theta. What about over here? If you plug in pi over 2, you get sine of pi, which is 0. If you plug in 3 pi over 2, you get sine of 3 pi, which is 0. So that's all gone. And our simplification becomes 3 times 3 pi over 2 minus pi over 2. 3 pi over 2 minus pi over 2 is pi. So we end up with 24 pi. That'll be the area of the full cardioid. All right, let's stop. Let's stop for a week. Let's stop for a week and some days. Well, have a great break. Great Thanksgiving. I'll see you in December. Please do lots of calculus, because you really have, there's only one more opportunity. So we'll come back, we'll do our review on Tuesday, we'll take our test on Thursday. I will, believe it or not, be checking email over the break, so if you do have questions, you can email me, I'll get back to you. And remember, in my math lab, there's only a couple of you that use the Ask My Instructor feature. You can always use that feature. You click the Ask My Instructor button, it sends me an email with a picture of the problem, so it's pretty easy. I think there's only 2 people in here that are using it.
Have a great day.
Yes, have a great break. Enjoy your holiday. Right? Hey man, you're a student. You don't really get a holiday.
Yeah,
The grind is on.
you know,